Section 5, Geometric Transformations. This goes back to geometry when we learned about these four major transformations that we have. It turns out that you can use matrices to perform those transformations without having to graph them. So if you understand how matrices work and how the geometry of those matrices work, you can use matrices to come up with the transformations very easily and a lot more quickly than using like drawing figures or whatever it is that you did in geometry class. So what are the four transformations that we used in geometry? Good, you finally figured out after 8 months that I usually put the answer to my question on the page. Yes, translations, dilations, reflections, and rotations. What is a translation? Moving. Everything moves. Okay, slide is a very bad word to use. Shift, a translation is a shift. Which way? Up or down or left or right. Or maybe up and right or something like that. Combination of horizontal and vertical shifting. Dilations, what are those? The size changes. The overall shape of the thing does not change. It's just that the scale of it does change. So dilations. Okay, fine. It's going to become bigger or smaller, but shape is the same. Does the shape change for translations? No, nothing changes. The object just moves. So shape and size stay the same. What's a reflection? All right, the word you use is a flip. A reflection is like looking into a mirror. You look in a mirror and you see your reflection. So a flip over a line. Does the shape change with a reflection? Does the size change with a reflection? No. So size and shape, same. And what's a rotation?
A spin.
Revolving about a point. Now the interesting thing about rotations is that point can be outside of the figure. Like if I have my pen in my hand and I rotate about my shoulder, then the object rotates. If I put the object in my hand and then I rotate about a point on the object, then the object rotates about that point. Rather than rotating in space, it's just spinning about itself. Okay, so rotations are a little unique. You can have two different types of rotations. But in either case, did the size or shape of my pen change? No. So shape and size is the same. So hopefully you remember all that stuff. We've been talking about a lot of these, actually. We've been talking about translations and dilations and reflections all year long with our like vertex form of a parabola, things like that. We haven't been talking about rotations at all this year, though, but we are now. All right, the first thing we're going to do is learn how to set up a matrix based on a geometric shape. And the easiest geometric shape to work with is, of course, a triangle. And we've already kind of worked with a triangle in a coordinate plane in the last section when we were doing or 2 sections ago, when we were finding the area of a triangle in a coordinate plane. We set up a matrix. Well, to do this, what we're going to do is we're going to identify the vertices of the shape. So here are my vertices. I should probably come up with some ordered pairs for each of those. So I'll start here. I have 4, 0. And then up here I have 1, 3. And then here I have -1, -2. And maybe I'll attach letters to those. A, B, C. Okay, So step 2 says write the coordinates in columns of a matrix. X coordinates are your top row, Y coordinates are your bottom row. So the dimensions of this matrix will be 2 by however many points you have on this shape. In this case we have 3, so we'll have a 2 by 3 matrix. Write the coordinates in columns. So I have point A is 4, 0. Point B is 1, 3. And point C is -1, -2. And that's how you set up your matrix for your geometric shape that you're talking about. All right, the first one that we're going to do is also the easiest one to tackle. Translations are very easy with matrices. Translate the figure 2 units to the left, 1 unit down. This is the same figure that we were just working with. So in geometry, what we would do is we would sketch this thing, and then what would we do? Move all the points, left 2 and 1 down. So let me put these ordered pairs on here again. I called this one A, this is 4, 0. This one I called B, and this was 1, 3. This one I called C, and that one was -1, -2. All right, now I'm going to change colors. And I'm going to place each of these new points. And how do we label a new point that we've transformed? With a prime, right? We call that a prime. So we want to go 2 units left, 1 unit down. So from A, I go 2 units left, 1 unit down. Here I am. I'm going to call that A prime. For point B, I go 2 units left, 1 unit down, and I'm going to call that one B prime. And for point C, I'm going 2 units left, 1 unit down, and I'm calling that one C prime. And then I can draw my shape, and this is pretty much what geometry was all about in that chapter, the transformations chapter. So I draw my new shape on here. Hopefully not terribly. There we go. It is exactly the same triangle, it's just moved a little bit. What are the coordinates of A prime? 2, -1. What are the coordinates of B prime? And the coordinates of C prime? Okay. So what are the new coordinates? I just wrote them down here. How can we write this as a matrix? Well, let me rewrite our original matrix. Remember, it goes x, y as columns. So for point A, I had 4, 0. For point B, I have 1, 3. For point C, I have -1, -2. Now for my transformed shape, I'm going to have a new matrix with new coordinates. So over here, for point A prime, I have 2, -1. For point B prime, I have -1, 2. For point C prime, I have -3, -3. How could I use another matrix to go from my blue matrix, my original matrix here, to my red matrix here? Add what? Exactly. If I add -2, -2, -2, and -1, -1, -1 to my original matrix, I get this matrix. Where did this -2 and -1 come from?
Moving it left and down.
I moved it left. That is in the negative direction, so that's -2 units left. -2 units. I moved it down. That's in the negative direction, so that's why I wrote -1 here. The math here on this is very simple. So hopefully you can kind of see how the geometry turns into the matrix, and now I have these coordinates sitting here without even needing this picture at all. So, if you're going to transform a matrix using translations, transform a figure using translations, set up a matrix of ordered pairs for all your points, add a new matrix, your transformation matrix, adding how much it shifts left or right, how much it shifts up or down, add them together, and you have your resulting ordered pairs. Dilations, remember, makes something expand or contract, basically. It makes it grow or shrink. The overall shape stays the same, but it has become either bigger or smaller. There's an excellent example of a dilation in your daily lives. Your pupils. You ever seen your pupils dilate? You've watched them dilate? Oh, that's messed up. Oh, look at that. I put pupils on there anyway. So dilations are just an expansion or contraction, just like your pupils. To perform dilations geometrically, multiply the lengths of the sides by a scale factor. That's how you did the dilations before. To perform dilations using matrices, multiply the coordinate matrix by a scalar. So it's very simple to dilate something using a coordinate matrix. All you got to do is multiply by the scale factor, and that's it. So, for example, dilate the above figure such that the perimeter is twice the original perimeter. That means I'm going to multiply this thing by a scale factor of 2. Then dilate to make the perimeter 1/2 the original. The interesting thing is, I don't know if you guys learned this or not, but if I dilate about the point 0, 0, I could draw lines from the point that I'm dilating by through each one of my vertices. Did you learn this before? No, I didn't draw the third one because that's just my x-axis. But if I'm multiplying by a scale factor of 2, then all I need to do is figure out this length here and then go that length again. So 1, 2. Up 1, up 2 to the left 1, up 2 to the left 1, over 1, over 2. There's my new figure. This actually makes dilations in geometry painfully easy. That's it. Now you have the ordered pairs, and you can figure out what the ordered pairs are from that. But that is the figure right there. It has twice the perimeter that it used to have. Okay, but we want to do that using matrices. So we need to set up the coordinate matrix. Multiply the coordinate matrix by the scalar. So the coordinate matrix is going to be my original points. I have a point right here that is 1, 0. I have a point right here that's -2, 2. I have a point right here that is -2, I can't read this, 4. -2, -4. So that makes my matrix what? -2, -4. Okay, now I'm multiplying by a scale factor of 2. So I slap that 2 out front, and then I send it in. And I get -4, 2, -4, 4, 0, -8. -8. And I screwed this up. This should be here. This is, thanks a lot, -1, -2. So this should be -1, -2. So that makes this -2, -4. Sorry, the original figure has these ordered pairs. So that's why this matrix was messed up a little bit. But now once you do that dilation, we have -4, 4, -4, +4, that's one of my ordered pairs that I knew I had. 2, 0, there's the second one. And then -2, -4, -2, -4, there's the third. So the matrix, as long as you don't pull a me and set it up correctly, works. Multiply by the scale factor. So let's do the other one. Dilate to make the perimeter half the original. What do we get? Tell me the matrix.
Well, that'd be half of
So that gives me,
And that gives you negative 1, 1 half, 0, negative 1 half, negative 1.
there you go. So those are the coordinates of your resulting points. Now, you probably want to label these like we would call this one A, this one B, this one C, so that this would be A prime, B prime, C prime, so that over here you knew what ordered pair corresponded to what point. That is kind of important. But that's the idea here. For dilations, you're just multiplying the matrix by a scale factor. Very easy to do. All right, the next one, a little bit tougher, and there's a lot of different reflections that we can do. So we're going to be on reflections for a little bit here. Develop matrices for reflections across the y-axis, x-axis, and the line y equals x. The first thing we're going to do is remember how we did this in geometry. So the first thing I want to do is reflect across the y-axis. To do that, we have a line of reflection here, reflecting across the y-axis. And then like if you were looking into a mirror, you would see yourself exactly on the other side, the same distance away from the mirror in the mirror as you are from the mirror in real life, perpendicular to the mirror. So from each of our ordered pairs, we're going to go from here over 1 to here. That would be our first reflected point. Let me call these points letters, A, B, and C. The coordinates here are 1, 0. For B we have 4, 2. And for C we have 2, 3. So I reflect across, and now I have A prime. I reflect across, 1, 2, 3, 4, 1, 2, 3, 4. Now I have B prime. And I reflect across 1, 2, so 1, 2, there's C prime. And we'll figure out those ordered pairs here in a little bit. So that's my figure. I'm just going to connect these dots here without a ruler, so forgive my wavy lines. That's the figure reflected across the y-axis. Now, what I want to do is talk about how these ordered pairs get generated. What is the ordered pair for A prime? Negative 1, 0. What's the ordered pair for B prime? Negative 4, positive 2. What's the ordered pair for C prime? Negative 2, positive 3. What happened to the original coordinates as they got reflected over the y-axis to form the new coordinates? The x values changed sign. Anything else happen? That's it. So all we need to do is create our matrix, which we know is going to be a 2 by 3 with these ordered pairs 1, 0, 4, 2, and 2, 3. We need to do something to make all of the x values change sign, all of the y values keep their sign, but none of the numbers themselves are going to change. Ones and negative ones. Yeah, what kind of matrix are we going to be dealing with here? What did you say? Identity matrix. So if I were to multiply this matrix here by the identity matrix, what would I get? I get exactly the same thing. Now to do that, I have to put the identity matrix over here because my dimensions have to align. 2 by 2 times the 2 by 3 gives me a 2 by 3. So my identity matrix needs to go on the left. This matrix times my coefficient or my coordinate matrix gives me exactly still my coordinate matrix. But now I want to change something here. I want the x values to become negative and the y values to become positive. Or, I'm sorry, not to become negative, but to change sign, and the y values to keep their sign. So what do I need to do? No. I want the numbers to stay exactly as they are, except for the top row here is going to change signs. Which one? Why the top one? Let's try that. If I multiply this out, I have the top row times the first column. So that would be negative 1 times 1, which is negative 1. 0 times 0, which is 0. Negative 1 plus 0 is negative 1. Did I change the number? Did I change the sign? Yes. Second one, first row, second column. -1 times 4 is -4. 0 times 2 is 0. I get -4. Third column, -1 times 2 is -2. 0 times 3 is 0. I get -2. Did I get the effect that I wanted? Yes. Let's check the bottom row just to make sure that nothing changed there. This time I'm multiplying bottom row times first column. 0 times 1 is 0. 1 times 0 is 0. Add them together, I get 0. 0 times 4 is 0. 1 times 2 is 2. 0 times 2 is 0. 1 times 3 is 3. Did the bottom row change? No. So the effect is all I did was change the top row by changing all the signs. This matrix right here is the matrix you will use to reflect any object over the y-axis without the use of a figure. All right, let's do reflecting across the x-axis now. So reflecting across the x-axis, this is my line of reflection. I have pretty much the same figure as I did last time, so my ordered pairs are the same. A is 1, 0. B is 4, 2. C is 2, 3. Now we're reflecting across the x-axis this time. What happens to point A? It stays the same. It's like if I had my nose smashed into a mirror, I would see my nose smashed into the mirror on the other side. It's not going to move. So it just stays there. That is A and A prime. B, though, goes 2 and then another 2, so that's B prime. And then C becomes C prime down here. So my new figure is this. The coordinates of B prime are 4, -2. The coordinates of C prime are 2, -3. And then the coordinates of A prime are the same as A. Now, what happened to go from the original figure to the final figure? The y-coordinate changes. So if my original coordinate matrix was not negative. Thanks. And I want all the numbers to stay the same except for I'm going to change some signs. Then that means what is my matrix on the left going to have to be? We're using the identity matrix, but this time we want the y-coordinates to change sign. So based on what we learned last time, putting a negative sign on that one should change all the y-coordinate signs and keep the x-coordinate signs the same. Do you think it works?
Oh, yeah.
Yeah, absolutely. So this is your transformation matrix for reflection over the x-axis. Okay, so that's 2 of them. We want to come up with the third one now, the reflection across the line y equals x. So the line y equals x is this line. You hate this one? That's terrible. I'm reflecting over the line y equals x. We are using the same triangle, so this is point A, and it's still 1, 0. This is still point B, and it's 4, 2. This is point C, and it's 2, 3. I'm going to change colors this time just so we're not confused. You're still reflecting perpendicular to the mirror. So from point A, I have to go perpendicular to the mirror, halfway across the square diagonally. So I'm going to land right here. That's A prime. For B, I have to go again, just 1 across. So I'm going to go 1 again, and that is B prime. What? For C, I have to go diagonally half a square. So I'm going to go diagonally half a square again, and that is C prime. So I connect all my dots, and I have my reflected triangle across the line y equals x. All right, let's come up with the coordinates now for A prime, B prime, and C prime. And since this is so cluttered, I'm going to write them over here. A prime is 0, 1. B prime is, okay, 2, 4. And C prime is 3, 2. So, just like before, what happened with our coordinates to wind up with our new coordinates? We switched the x's and y's. So let's go over here now and try to set up a problem that's going to make this happen. We need to come up with our ordered pairs. So our coordinate matrix, which is still 1, 0, 4, 2, and 2, 3. We're going to multiply times something on the left, just like before. Before it was the identity matrix, so let's see if we can figure something out that will allow us to switch the x coordinates and the y coordinates. Nope, because if I multiply by just 1, 0, 0, 1, the identity matrix, I'm going to get the exact same thing. I don't want the exact same thing. So what kind of numbers should I pick? Like 5 and 10? Okay, 6 and 10. Is that going to do it for me? No. 2 and 4. What's that going to do? It's going to change my numbers. Do I want my numbers to change? Did my numbers change here? No, they just switched. So I need to use 1 still. I need to use 1 still. And I need to use 0 still. You think? Let's try it. Let's try it. First row, first column. 0 times 1 is 0. 1 times 0 is 0. We get 0. Well, that's a good start. We wanted 0. Let's do the bottom column now. Let's do this spot right here. So that would be bottom row, first column. 1 times 1 is 1. 0 times 0 is 0. Add them together, I get 1. Well, that's what we wanted. So it seems like it worked. Let's keep going. Second position here. 0 times 4 is 0. 1 times 2 is 2. Bottom position. 1 times 4 is 4. 0 times 2 is 0, so we get 4. It worked. And the last one, 0 times 2 is 0. 1 times 3 is 3. 1 times 2 is 2. 0 times 3 is 3, so we get 2 here. Is that the matrix we were looking for? Nice job. So this is the transformation matrix for a reflection over the line y equals x. Okay, let's answer the question at the bottom here. Using what you've learned from these reflections, what is the reflection matrix going to be for reflections over the line y equals negative x? What do you think? It's the same matrix?
No, because you have to put a negative 1 or a negative 1 on the bottom.
Can I clear this?
Yeah.
Okay. The line y equals negative x is this line. If I reflect over that line, then this point will go here. This point will go 1, 2, 3, 1, 2 here. This point will go 1, 2 and a half, 1 half, 1, 2. It goes there. So here's my figure. What happens? The ordered pair here, 1, 0, becomes 0, negative 1. The ordered pair here, 4, 2, becomes negative 2, negative 4. The ordered pair here, which was 2, 3, becomes negative 3, negative 2. What's happening to my numbers? They're switching position and changing sign. So that means my matrix has to both flip their position and change their sign. So if this is now negative x up here, my coordinate matrix is still 1, 0, 4, 2, 2, 3. my reflection matrix will be, that's correct. So now you can reflect over 4 things: the y-axis, the x-axis, the line y equals x, and the line y equals negative x. What I want you to do now is take what we've done up to here and fill in this summary table. This is your reference for how to do these reflections.